Excellent. Thank you, Andrew. Just to introduce myself, I'm Randy Kershane. I'm a principal research scientist and one of the co-directors for the Concrete Sustainability Hub here at MIT. And what I wanted to talk about today was to give you an overview of the work that we've been doing to understand the impact of what are called cool pavements, both on mitigating urban heat island effects and on the impacts of climate change. And, one of the things I kind of want to tell you, one of the conclusions from right here at the beginning, which is that one of the more interesting things that we've found is that cool pavements can both cool cities and cool the climate. That is, in most contexts, have a net climate benefit. And another way that people often ask us about that result is that, sure, I could imagine that cool pavement has some climate benefits, but of course, there is an embodied burden. There's burden of creating the pavement. And so do the benefits outweigh that burden? And I'm going to try to make the case, and through the results we've had so far, is that the answer to that is, in the vast majority of contexts, the answer is yes. Before digging into the results specifically, though, I kind of wanted to take a step back and sort of remind us, why are we talking about cool pavements? What's relevant about cool pavements? Here in the Boston area, we had yet again one of the warmest summers on record, but of course, nothing compared to, you may remember back in June, these very extreme temperatures that were felt in the Pacific Northwest. And if you kind of pick out some of the urban areas on that map, you can see that many of the urban areas saw especially high temperatures. And that was quite unusual, but there's a lot of science coming out to say that historically abnormal condition may not be that unusual going forward. IPCC came out with a report this year saying that these intense heat waves are going to be happening much more frequently, maybe every decade, and that cities, urban areas, feel the brunt of that with even more intense heat. So sometimes we might think of intense heat as simply annoying, but what are some of the real impacts of it? Well, directly, the impact of more extreme heat is we spend more energy on cooling our structures. And there's an estimate that every degree Fahrenheit increase in air temperature translates into a growth in electricity demand by about 2%. And obviously, for the time being, translates into more greenhouse gas emissions into the air. But frankly, much more acutely than that is that oftentimes we don't realize, but if we look at the National Weather Service data on hazard events, point of fact, heat-related deaths are actually higher on average per year than any other weather-related fatality. So this is a problem that matters and one that needs to be tackled. Fortunately, cities do have a number of solutions that they can turn to: increasing vegetation, implementing cooling centers. But what we've been looking at here at the Hub is, can cool pavements be a part of that solution portfolio? And in particular, does it both provide cooling benefits locally and climate change benefits globally? So what's a cool pavement? A cool pavement is really just exactly what it says. It's one that's going to stay cooler in the sun, when it's exposed to the sun, than a conventional pavement. And that technically, what that translates into is one that reflects more energy, therefore stores less heat, and then has lower surface temperature. The metric that we use to measure that first point, the sort of the key point in that causal chain, which is, does it reflect more energy or not, is something that we call albedo. And it's just a technical term to represent the fraction of the energy that is radiated onto a surface that is reflected back. And so because it's measured in that way, a lighter surface that will reflect more energy has a higher albedo than a darker surface that absorbs more of that energy. And so what I'll talk about in oftentimes what you'll hear me in the balance of the presentation is talk about is what is the implication of shifting to a higher albedo pavement. And that is, a metric of it being cool pavement. Another thing that makes this, one of the things that makes this a really interesting question is that there are actually a number of different strategies to realize a cool pavement, to realize a higher albedo pavement. One that is probably seeing, there are a lot of trials going on currently, is the application of reflective coatings. That's what you see here on the left of the slide. And this can be done to effectively any existing pavement. We've looked at that as part of this study, but what we've also looked at is shifting to alternative binders. That is, like using concrete pavements that inherently have a higher albedo than an asphalt pavement that they might replace. And then we'll also look at some special variants of both concrete pavements that make use of different aggregates or different binders to actually achieve an even higher albedo. You'll hear me refer to that as sort of reflective concrete. So what are specifically the questions that we've been asking about this portfolio of solutions? And there's really three. One is, what's the potential for pavement albedo to actually lower urban air temperatures? Secondly, how does context, and what I mean by this is sort of urban context, the setting in which the pavement is placed, how does that affect the impacts of raising pavement albedo? Partly because of time, we won't dwell as much on that, and I'd be happy to follow up with people if they have more questions about it. And then third and finally is sort of the ultimate question, which is, do cool pavements create global climate benefits or burdens? That is, like I said at the beginning, do the climate benefits during use outweigh any additional embodied impacts to create the pavement? From a research perspective, this is an interesting question because the impact of changing pavement albedo is complicated. It's complicated because, and you'll sort of see this in some of the results, is that the effects of making that change manifest in many different ways. There is literature that has pointed out that albedo change can have feedback and actually change the regional climate in an area, increase or decrease cloudiness, change patterns of rain. It somewhat directly affects the climate by if we reflect more energy, then there's less energy that is retained within the Earth's atmosphere. So that change is something that's referred to as a radiative forcing. I'll sort of come back to that in a minute. Another way in which this behavior is complicated is that if we change the temperature in a neighborhood, that obviously you would expect that to change the energy use of the buildings in that neighborhood. But we also change the amount of energy that's sort of reflected around in that neighborhood, which also would change energy use in buildings. And then finally, if we make any kind of, just like any type of material change, whether we're talking about a coating or shifting to a concrete pavement, there are many other aspects of the life cycle, the supply chain, how it affects other aspects in use, and obviously end of life that come into play. And so in order to answer this question, we actually have to look at all of these issues. But I'm going to, as I kind of walk through our key questions here, we'll sort of emphasize certain aspects of this more. And first, just as a kind of a reminder, our key questions are, again, what is this potential for pavement albedo to lower urban air temperatures? And that's actually the issue that we're going to, oops, sorry, technical difficulty there. Secondly, how does context affect the result? And finally, what is the net result? But let's dig into this first question. What is the potential for albedo change to lower urban air temperatures? To answer this, this is a piece of work that was wrapped up a few years ago. We actually turned to colleagues here at MIT that focus on regional climate modeling. And we actually worked together to build or to apply a climate model of the entire continental United States with part of the model being at lower resolution, like you see on the left, to capture less urban areas, and then a high resolution model that was intermeshed with that to look at behavior within urban areas. And specifically what we did is we took this model and we simulated how climate would evolve over a 20-year period under two different conditions. One, where urban albedo stayed as it is today with an average of about 0.2, and in a case where we raised that from 0.2 to 0.4. So we had a higher albedo within the paved surfaces in the urban area. And what we found is that if we look across the average of that 20-year simulation, first, just sort of look at this first column of results. What we see is an average change in summer temperature of about 1.5 degrees. It varies a little bit depending on the specific area. And, that doesn't sound like a lot, but I think you can understand the implications of it more if you look at the other two columns. And so that 1.5 degrees in average max temperature translates into a significant drop in the number of heat waves that were experienced over that time period, and in the number of extreme heat days. That's heat days essentially over 100 degrees, 106 and specifically. And so that small change, 1.5 degrees, actually translates into real change in terms of these more extreme events. So the answer to our first question here is it would appear that changing the albedo of urban pavements would be expected to lower urban temperatures in a meaningful way. So what about our next question? How does the context, the urban configuration, alter the implications? And so to better understand this, first off, just let me remind you of sort of the key relevant behaviors that are kind of going on in the urban setting. First off, when we change albedo, whether this is in an urban context or not, we change the Earth's energy balance. If we're reflecting more out of the atmosphere, they were retaining less. And again, as I mentioned earlier, this is something referred to as when you make a change like that, it's referred to as a radiative forcing. The other thing that's going on is when we change ambient temperatures, or when we change the amount of radiation that is reflected from a pavement, say, to the adjacent buildings, we change the amount of energy that's needed to cool or heat those. And sort of the implication of these is can counter each other in a way. So when we talk about the radiative forcing, if we increase albedo, we create a so-called negative radiative forcing, and that has the equivalent of atmospheric cooling benefits. But in the urban context, things are a bit more complex. If we increase the amount of radiation that's being reflected from the pavement onto the building, we would anticipate an increased cooling load, but a reduced heating load. When we change local air temperatures, we actually anticipate the reverse. If we lower temperatures, we would need less cooling and therefore increased heating. And so ultimately, the question kind of comes is, what would be the net effect? So to answer this, we had to build models that would allow us to capture each of these. In an earlier piece of work, we have presented how we have created a statistical model that allows us to estimate what the radiative forcing impacts would be for albedo change anywhere within the United States. The reason that you would see different radiative forcing implications from albedo change depending on location are for several reasons. One is that the further you get away from the equator, the shallower the angle at which solar radiation would hit a pavement, so the impact is less. The amount of cloudiness in a particular area, the amount of pollution in a particular area, each of these can moderate that effect. And so we have constructed this model that allows us to make that estimate. And what you're seeing here are some annual GWP savings, so CO2 equivalents of making that radiative forcing change. The impact of this, if we were to go in and take all of the pavements in the United States and raise their albedo by 0.2, it would be the equivalent of removing about almost 4 million, or about 4% of passenger cars off the road. And I'm sorry, or just around 3% of passenger cars. There are some states like Texas where that benefit is even more, where that albedo change would be the same as possibly taking a little more than 4% of the fleet off the road. So you can start to see how that albedo change, increasing albedo, has some climate benefits that are interesting. Now, what about the impact on the urban environment? So to understand how albedo change in an urban context would change our energy use and therefore emissions, what we did is we created thousands of different hypothetical neighborhood configurations, and we used some systems applied within urban planning to categorize those different types of neighborhoods into what are called local climate zones, or you might, in some of the later slides, you may see LCZ as an abbreviation. But effectively, a local climate zone is simply like a category of configuration in an urban setting. Maybe it's compact and very dense and tall. Maybe it's shorter buildings that are more spread out. But in the end, what we did is for each of these types of neighborhoods, we created many different variations, taller buildings, more spread apart streets, and then we modeled those neighborhoods in detail. We looked at what would happen if the local temperature was different, what would happen if the local albedo was different, including tracking the way in which solar radiation would reflect from a pavement to a building to an adjacent building and so forth. Once we had done all those simulations, we created a machine learning model that would allow us to sort of fill in the gaps, that would allow, say, if a neighborhood is somewhere in between these two, what would we estimate that energy implications would be? And so once we had that, then we could take that machine learning model and then apply it in real neighborhoods and say, well, the configuration of this neighborhood is most like this other one that we simulated, so we would anticipate that that benefit or that impact in that particular neighborhood. And this is just sort of a snapshot of applying that model to a couple of blocks of buildings within Boston. So we, fortunately, because GIS information is available, we can actually do this. We can go in and look at the configuration of the neighborhood around every building in Boston, or you'll see in a second that we did a similar thing for the city of Phoenix. You can start to see just from this little snapshot, though, how context can matter, that either the height of the building or the amount of the building that faces the adjacent street can change the result. We can see examples where in this plot, we're plotting carbon benefit from a change in albedo. So if you see an arrow that's green and going up, it means that in that case, heating demand went down. So that meant less emissions associated with heating, or cooling demand went down. So there was an overall benefit. And we might have ones like this one in the lower right, where there was some benefit from reduced heating, some negative from increased cooling, but in net there was a benefit. Or there are some buildings like this one in the upper corner where the increased cooling load outweighed the benefit from heating. So you can see that the context matters a lot. The specifics of the building, the specifics of the neighborhood cause this result to vary considerably. So again, we did this for the entire city of Boston. And so what are some of the things that we saw? So first off, when we look across the city of Boston here, so a green on this map means that on average within that neighborhood, specifically it's something referred to as a census tract. So on average within that census tract, we see a net benefit simply from albedo change in this context. We'll come to other impacts from pavements. Nevertheless, from one neighborhood to the next, you can see differences. You can see ones like down here in the lower corner where there was a radiative forcing benefit, but a negative impact on cooling, but a benefit on heating. And then this more dense neighborhood here where we see sort of a reverse behavior. So again, the specifics of the neighborhood can change the specific magnitude of these different aspects of it, whether it's radiative forcing, its impact on cooling, its impact on heating. Interestingly, in Boston, we saw that the changes, the order of magnitude of changes from radiative forcing, from cooling changes and heating changes were all roughly in the same order of magnitude. that ended up being different in Phoenix. Just for time, I'm not going to go into the details as much, but just as a kind of a quick summary, what we saw is that in the dense urban neighborhoods in Boston, generally the energy demand, the BED, building energy demand change, was larger than the radiative forcing change, both of which led to benefits. And so there was a net benefit or savings in global warming potential equivalent. In most other neighborhoods, that was reversed, but again, both were savings. And so overall, we had savings. In Phoenix, we saw a different story. Again, these are just the impacts of the albedo change. We'll get to the rest of the life cycle in a second. Maybe if I start down in the lower right, we saw in the majority of Phoenix, where it's more sparsely built, a net savings, primarily driven because of the radiative forcing benefit. In the really dense urban neighborhoods, we could end up with cases where there was a net burden. In other words, that the change in building energy demand was larger than the radiative forcing gain. But of course, this is only part of the story. And our third part of our question is, when we take a life cycle look at these pavements, what is the total net benefit or burden associated with installing a cool pavement? And now, when we talk about life cycle, what we're asking here is all of the effects of making that material choice. So that goes from everything from materials production to construction of the pavement, the use phase impacts, as well as any impacts that derive from end of life. Now, one of the use phase impacts, the one that we've already been focusing on, is that while the pavement is in use, it has these albedo-related impacts, radiative forcing and changes in building energy demand. But one that I haven't brought up before, but one that we have captured in the analysis I'll show here next, is what about the impact on the vehicles that drive on those pavements? It's something that we refer to as the pavement vehicle interaction effect. And that manifests in two ways. One is that the roughness of the pavement over time, so the rougher the pavement is, the more time I spend with my wheels going up and down instead of going forward, that leads to more energy use. Or the stiffness of the pavement. So the stiffer the pavement is, the less that a heavy vehicle indents that pavement, and the less energy has to be spent in overcoming that indentation of the pavement. So when we build out models that capture all of these effects, as well as looking at the emissions associated with materials production, what is it that we see for Boston and Phoenix? So bottom line is that we see most of the pavements in Boston and Phoenix would provide a global climate change benefit if they were switched to a cool pavement. That what you're seeing here, green, implies a total life cycle savings. So it's benefits in terms of albedo effects and pavement vehicle interaction that outweigh any additional embodied impacts that are incurred in order to realize that cool pavement. You see a few places in Phoenix where that isn't the case, and we'll sort of unpack some of those here in just a second. So let's dig in just a bit on what are some of the results we saw from Boston. So remember, this result comes from modeling the impacts on every building and every street segment that sits in front of each of those buildings. And so we chose a couple just to kind of see what types of implications there are from making this kind of change. In particular, what we looked at was 4 different alternatives. One is a flexible pavement, typically an asphalt pavement that makes up most of these urban pavements. That's the first bar that you see there. A switch to a rigid or conventional concrete pavement, a switch to taking that flexible pavement and putting a reflective coating on it, or fourth is making use of a concrete mixture that would have an even higher initial albedo than a conventional concrete mixture would. And the initial albedo of each of those is actually shown in parentheses just next to the name. You can see a few things here. One, the blue part, I should also point out, this is a local road with a very low daily amount of traffic, about annual average daily traffic of only in 600s. The blue part here represents the burdens associated with materials and of constructing the road. The other colors represent the use phase impacts. Remember, the albedo change impacts typically are benefits. So unfortunately, bar chart sort of fails us here. They're shown as negative. So what you want to look at is not the height, the total height of the bar, but because of this negative part, you want to look at these points. The points represent essentially the final result. And you can see in this case, the lowest impact would come from a reflective rigid alternative, a higher albedo rigid alternative. If we look at an interstate example in Boston, you see the actually the same net result, but a very different portfolio of effects. Here we see that, and also I just point to a difference in scale here. We're looking now at an interstate in Boston, much higher average daily traffic, and a very different portfolio of effects, as I said. Again, the materials impacts in blue, the use phase impacts in orange and green, effectively. And so comparing these two, you can see for that local road that the albedo-related use phase impacts are actually larger than the pavement vehicle interaction. So the green area is larger than the orange. When we look at a higher traffic road, that inverts, and these pavement vehicle interaction effects actually are much larger than the albedo-related effects. So it's, again, a case where context really matters. To understand this, you have to look at it in a fair amount of detail. In Phoenix, we get some different types of behaviors. Generally, what we see is that pavement vehicle interaction effects in most of the contexts tend to be the larger of the two. I saw a question pop up there, Andrew, so let's just keep track of that one. On the left here, I'll just start with this one. You can see a case, fairly typical case in Phoenix, where you have a very large amount of pavement vehicle interaction related impacts. We have a sort of moderate amount of albedo related impacts. And in this case, essentially a tie between going with either a conventional rigid or a reflective rigid. Again, you're looking for the dot as sort of the final number here. Now, in Phoenix, there are some neighborhoods like these pinkish neighborhoods here where we have a fair amount of density. In the case of density, it means that the albedo effects are somewhat different, and you have very low traffic on the road, so therefore the pavement vehicle interaction effects are quite small. And so we have a few of these neighborhoods where staying with a conventional flexible pavement actually has the lowest impact. And so just to kind of summarize those, when we look overall at the total life cycle impacts here, what we see is that the cool pavement design is almost always preferred. That is that it not only lowers local urban temperatures, but also provides a climate change benefit, or is what is worded here is the lowest global warming potential score, if you will. For Boston, a higher albedo pavement is preferred in all cases. The lowest impact solution, or the highest benefit solution, if you will, changes depending on the neighborhood. In about 55% of the lane miles, it's clear that a higher albedo rigid pavement is the best solution. And in a little less than half, there's a bit of a statistical tie between either going with a reflective rigid or reflective flexible pavement. Those ties will essentially, they require a little bit more local information about the specifics of the neighborhood, specifics of the pavement, to be able to tease apart which would be the best. When we look at Phoenix, what we see is, again, cool pavement design is almost always preferred in the vast majority of lane miles. So if you add up the 73% and the 9%, we get 82% of the cases that a rigid pavement is the low GWP solution. In 73% of that, it's a higher albedo rigid pavement, and in about 9% of that is a conventional mixture. Most of the rest are one of these statistical ties where we need a little bit. So that 17% is we need some more information to tease apart the best option. And then about 1% of the lane kilometers, we have a case where staying with a flexible is the climate preferred option. And so just, yeah, one thing I do want, this is another way to kind of look at this. We often get this question, as I mentioned at the beginning, which is, we could see there being climate change benefits, but does that outweigh the burdens and the burdens of installing the pavement? And so again, as I've sort of highlighted in the last few slides, the specifics will change from neighborhood to neighborhood, but this is a fairly typical result, even when we look across the two. And that is the way to see this balance is if maybe just focus on these first two bars here. So if we go from that lower albedo option, the flexible pavement, to a higher albedo rigid, we do incur an embodied burden. There is additional burden for installing those materials, and that is, you can see that by the difference in the blue bars. But compare that to the change in the orange and the green bars between the two. And those are the benefits that occur during use phase from making that change. So again, context will change the specifics of this, but when we are showing a result, sort of a green neighborhood, if you will, it's one where that balance is like we're looking at here, where there is a small additional embodied burden, but it's outweighed by the benefits during use. So just to summarize what we've learned, what we've seen from the regional climate simulation is that there is real potential for higher albedo pavements to lower urban air temperatures, maybe on average of 1 to 2 degree decrease in summer maximum temperatures, which translates into significant decreases in extreme heat events. Does context matter? It matters a lot. It doesn't matter. So as you saw from the sort of end result, in the vast majority of cases, all of the cases in Boston and almost 99% of the cases in Phoenix, that going to that cool pavement option has both local benefits and climate benefits. The way that context matters is specifically which solution is the best to go with. And so, we hope that these tools will allow cities to sort of screen for neighborhoods where they have sort of an obvious solution, and then ones where there is some question, and then maybe do a deeper dive for those particular neighborhoods. And then finally, for our overall question, do cool pavements create global climate benefits or burdens? And as I just said, in almost all of the cases, those use phase benefits outweigh any additional embodied emissions for creating the cool pavement. The only cases where we didn't see was in that high heat city like Phoenix, where you had a very dense neighborhood, so the albedo effects are limited due to shading, and that also happen to have very low traffic. And so going to a rigid pavement has relatively small PVI benefits. But other than that, we see it in a benefit overall. So one way to kind of summarize this result is that in almost all cases, the cool pavement can both cool the city, reduce the urban air temperatures, and cool the climate, provide a net climate change benefit. And so with that, I will wrap up and maybe ask Andrew, who I'm hoping's been keeping track of the questions that have been coming along.
Absolutely. So our first question is about whether the albedo change from 0.2 to 0.4 refers to the average urban albedo of roofs and pavements, or if that change refers just to pavement albedo.
Yeah. So when we did that simulation, you can imagine that. So I'm assuming that what we're talking about, is about sort of the regional climate simulation. When you do analysis at this scale, it's obviously difficult to isolate the roofs and the pavements within a given city. So what we did was we did our best to estimate what the fraction of pavements would be as opposed to the fraction of roofs, and only made that change for the pavement fraction. So, again, at this scale, there will be some errors from city to city in terms of what that fraction would be, but our attempt was to only change it for the pavement fraction, not for all roofs and pavements. But that's a good question. Sorry for not clarifying that earlier.
And one further question is regarding the glare that might be generated from more reflective pavement. So would that present a concern? What might be some of the impacts of that?
Mm-hmm. Yeah, all of the options that we've looked at are alternatives that exist today and don't seem to have significant glare impacts. I mean, we're not talking about going up to very extreme albedo levels here. We're looking at albedo levels that exist today. And so I think, obviously in a very specific context, that may be something that could be looked at, but it doesn't generally seem to be a problem with these.
And then one other question we have here is, what about the nexus in pavement, buildings, and vehicles?
Yeah, I think that what's really interesting about this question is kind of that nexus, if you will. If how do you answering the question of the impact of a technology change like this requires us not to just look at the change in the pavement itself, but how that pavement interfaces with all these other urban systems, whether it be the buildings, whether it be the vehicles. And so, yeah, I think that's probably the most interesting aspect of this. Andrew, do we have
So
another
one
one?
question is, can we achieve high albedo as high as 0.6? Is that feasible?
Yeah, it's not something that we've looked at. I think that I think that's an interesting question, and I think also, as the earlier comment brought up, as you get into the more extreme albedos, there may be other issues that one needs to look at, but it's not an option that we had looked at within this.
So one further question here is, what's the uncertainty associated with developed models at the micro and macro scale when you consider the interconnectedness of all the different elements that you're looking at?
Yeah. So I don't know that I don't have a quantitative answer for you. I can follow up with someone because we certainly have documented that, but I just don't remember it off the top of my head. But when we have results like this in Phoenix or this within Boston, the reason that we're talking about these statistical ties is because we've tried to be as honest as possible about what the uncertainty is in these, which can be fairly significant. But you probably saw from some of the results is that the differences themselves can also be fairly significant. So when have a result like this that says that reflective rigid is the preferred option, it means that it is statistically defensible. In other words, that even once you account for a fairly significant amount of uncertainty, that it is resolvable as preferred from the other alternatives.
Here's a quite timely question. It's, how might the current pandemic we're experiencing impact some of the results we're seeing here?
Yeah, I think that, yeah, it's an interesting question. I guess there's a couple of ways. I mean, one is that it probably shifts the pattern of building energy use, right? So, we tried to model typical patterns of energy use within these buildings. And so If people are working more from home, then residential buildings are going to see more energy use than in urban centers. So that could shift results somewhat. I think the thing that at least seems to be not true in Boston anymore is like certainly during the pandemic, the traffic patterns were very different and typically much less. And so in that kind of a setting, these pavement vehicle interaction effects would be reduced. But I can't speak to for every city, but that pleasant change seems to have disappeared here in Boston. So I don't think we are seeing any kind of lasting effect from that. But yeah, so I think those would be the two main, probably the pavement vehicle interaction one being the bigger change.
And then in this work, the hub has looked at the scale of the United States and then cities. How might that get scaled to a global scale? And what are some of the challenges associated with that?
Yeah. I think that so the applying these models to so obviously, we try, it's probably fairly obvious why you would choose Boston and Phoenix. I mean, we're trying to choose a city that's where more of its energy demand comes from cooling and one where more of its energy demand comes from heating in order to sort of give at least a fair spectrum. But it is a fair question in that, like, just the urban morphology, even if you're in a climate similar to Phoenix, urban morphology meaning that the arrangement of the buildings is very different. The grid is very different. Um, the it would not be time consuming now that we have this process to sort of scale a model like this to a different location, um, to give a more specific result. I think that by looking at such a bookended set of climates, it does imply that for any a city with a reasonable amount of traffic, um, at least a typical level of emission associated with their grid, that they would this is worth looking at because it seems to have a benefit even in a fairly disparate set of contexts. So the what would need to happen is that we would need to adapt these machine learning models that we develop to that more specific climate context, and then it would be very rapid analysis to do. But it's a relatively scalable approach.
So one question I got in the chat bar is about the embodied global warming potential impacts of some of the paving actions. So what about a full-scale reconstruction? What about overlays of some kind, and how might that have cascading impacts in terms of albedo or pavement vehicle interaction?
Yeah, I think that to me, we try to look at as many things as we sort of had the resources to do. But if there was one that I would like to fold into this, it would be probably looking at sort of concrete overlays, so rigid paving overlays. You'd have we're talking about a thinner pavement cross section or depth than a full reconstruction, and so therefore you would end up with a lower embodied benefit, possibly not quite as much stiffening as you would get from a full reconstruction, but most of that benefit. And so that would tend to tilt things towards even more situations where that cool pavement option was one that was both cooling the local climate and providing climate change benefits. So I think that's certainly an interesting solution to also fold into future work, because that overlay gets you almost certainly gets you all of the albedo related effects and lessens the embodied impact and gives you most of the PVI effects.
And we have another question here about cost. So how might some cool pavements lead to your increased agency cost over time? And have you looked at the return on investment of cool pavements versus other mitigation measures that an agency could consider?
Yeah, I think that is the next important piece of work here. I mean, so you know, the short answer is we haven't looked at it. I think that one of the what I do know is that for implementing a rigid pavement alternative, which, you know, again, like in this case for Boston, in most of the cases has the lowest climate change impact. You know, typically represents five. There are some cases where it's the same, possibly even less, but on average, maybe 5 to 10% more upfront investment, typically with some lower life cycle costs that go along with that. But I think that would be I think that is an important next step, is to sort of look at what that return on investment would be. You know, I think the other thing to keep in mind in that is that cities do need, they will be maintaining their pavements, right? So it's a question of, can they make better decisions in those maintenance events to either put in different materials or different solutions to generate these benefits as well.
One question we have here is how much of the benefits we're seeing here derive from switching from asphalt to concrete, or derive purely from switching from asphalt to concrete?
Sorry, can you say the restatement again? Sorry.
Yeah, let me. So is there a way to attribute how much of the results here are purely from the change in albedo and how much accrue from switching from asphalt to concrete?
It's certainly something that we could pull out. I don't have a number off the top of my head to say that, because we tried to look at this, the whole picture, and so those are all the numbers that I could probably cite from you most quickly. But that's, if someone wanted to email me about that, I'd be happy to follow up. I just need to dig that number out.
So one further question is, when you have really tall buildings in comparison to the width of the road, you have a high aspect ratio. How can you make sure that the incident radiation escapes the urban canyon?
Yeah. So part of the reason that we looked at all of these different neighborhood configurations was to try to simulate those different kinds of contexts, you know, to simulate, in, like the question implies, you have different amounts of convection, you have different reflections going on in a setting like a more suburban setting where there's a lot of mixing and there's but maybe less incident radiation change on the adjacent buildings, whereas in maybe a more dense setting where you have less convection, less mixing, and more of that. So we've part of the reason for running these simulations of all these different neighborhood configurations was to try to isolate those types, or try to understand and capture those types of effects. And it's partly why you do see differences between people that are maybe not as familiar with just a random map of Boston and Phoenix may not initially pick it out, but what you're seeing in like a map, let's bring one of these up. Sorry, let me do this more efficiently. You know, when these areas in Boston, which are darker green as opposed to these lighter green, these are the denser areas as opposed to the less dense areas. So that does, you do see that impacted. And again, we've tried to capture within the modeling that we've done how it changes shading, how it changes the amount of heat that's retained, and tried to reflect that in these results. Any more questions, Andrew? You're on mute, so if you're telling me an awesome question, I'm not hearing.
Oh, I apologize. So the final question we have here is, do you have cost analyses of cool pavement designs and construction versus traditional pavements?
Yeah, only that upfront cost estimate that I gave before, that, you know, typically in the 5 to 10% additional investment for a rigid pavement, for a local rigid pavement, as opposed to the investment for but it's if folks wanted to follow up again with us on that, I think we can connect them up with the right resources to get them some more precise numbers on that.
And we have another message to the chat bar. So we've looked here at urban areas, and so how would pavement vehicle interaction and albedo benefits accrue in rural areas on rural road networks?
Yeah.
And have you looked
Yeah.
at those benefits in the context of life cycle?
We have. I mean, it's certainly a simpler analysis to do. I mean, the real complexity of this analysis is trying to capture the impact on the buildings. When you look at a more rural setting, generally, you know, that map of the United States where sort of the whole map was green is reflective of the fact that increasing albedo in a rural context has a climate benefit, just sort of unambiguously. And then if you go to a higher performing road, so either stiffer or less roughness or both, that will have a PVI benefit. In other words, it will reduce excess fuel consumption and therefore lead to less emissions from either the grid or from fuel combustion. And so in that more rural context, it's generally an unambiguous benefit of making these kinds of switches.
Do the attendees have any further questions? Because that's the extent of the questions we've received so far.
Maybe we let people get 4 minutes back for their day, and I just say thank you for the opportunity. And you know, for those folks that I wasn't able to give you a specific answer, I do mean it, Andrew, and I mean it. You know, email us, and we're happy to either answer it ourselves or try to connect you up with the right person to get you an answer. But thank you again.